When ultraviolet B light strikes the skin of most mammals, it triggers an immediate molecular reaction within the epidermis. In humans, sheep, and cattle, this radiation triggers the photolysis of a specific compound called 7-dehydrocholesterol. This reaction creates pre-vitamin D, the crucial first step in hormonal synthesis. Canines possess a distinct biological anomaly. Their skin contains virtually no measurable concentrations of 7-dehydrocholesterol. If you compare the cutaneous synthesis of a rat or a human under direct sunlight, the conversion is highly efficient. In dogs, the UV-mediated conversion rate is practically non-existent. Changes in environmental temperature, the presence of cellular lipids, or specific skin proteins cannot compensate for this absolute lack of the necessary precursor compound. As a direct consequence, dogs cannot use sunlight to synthesize their own vitamin D. They must ingest it entirely through their diet in the form of cholecalciferol, known as D3, or ergocalciferol, known as D2. This evolutionary trait makes dogs obligate dietary consumers. The entire burden of maintaining their internal hormonal balance rests squarely on the specific components of their daily food intake. The way we view this nutrient traces back to 1918, when Sir Edward Mellanby first identified it, calling it an accessory factor. Early veterinary experiments focused exclusively on curing ricketic puppies by administering therapeutic doses of cod liver oil. Because of these early visual results, standard dietary guidelines, including those from the National Research Council, established canine vitamin D requirements based strictly on preventing observable bone abnormalities. For decades, an unbalanced diet lacking vitamin D was feared primarily because it triggered nutritional hyperparathyroidism, leading to a condition called fibrous osteodystrophy, or rickets. Modern veterinary data demonstrates that this purely skeletal model is dangerously incomplete. Preventing rickets represents the absolute minimum biological threshold. Treating vitamin D solely as a calcium regulator ignores its actual function as a critical systemic hormone required for total organ health. To understand its systemic impact, we have to trace ingested vitamin D3 as binding proteins carry it from the digestive tract straight to the liver. Here, the liver utilizes an enzyme called 25-hydroxylase to transform the raw vitamin into 25-hydroxyvitamin D, or calcidiol. This newly formed calcidiol exits the liver and circulates into the kidneys. Inside the kidneys, an enzyme known as 1-alpha-hydroxylase executes the final conversion, creating 1,2,5-dihydroxyvitamin D, or calcitriol. This is the most active, naturally occurring form of the hormone. Measuring calcitriol directly in a clinical setting is incredibly difficult. It is hydrophobic, it circulates in microscopic picomolar concentrations, and it degrades with a short half-life of only 4 to 6 hours. By contrast, the intermediate metabolite created in the liver, calcidiol, is highly stable and remains in the bloodstream with a half-life of 10 to 21 days. Therefore, measuring serum 25-hydroxyvitamin D concentrations is the globally accepted, reliable marker for determining a dog's true hormonal status. By cross-referencing this marker against parathyroid hormone and C-reactive protein levels, researchers established that systemic sufficiency requires a target clinical range of 100 to 120 nanograms per milliliter. Evidence shows that toxicity risks generally do not become a clinical probability until levels push above 150 nanograms per milliliter. Tracking serum calcidiol is the only empirical method veterinarians have to verify if a dog's dietary intake is successfully fueling these metabolic pathways. Once active, calcitriol operates far outside the skeleton by binding to specific vitamin D receptors distributed across multiple organ systems. In the heart, individual cardiac myocytes possess these distinct receptors, alongside a calcitriol-dependent calcium-binding protein required for muscle function. Cardiac outcome data shows that low serum calcidiol is definitively associated with higher mortality and poor clinical responses in dogs suffering from congestive heart failure. The deficiency acts directly as a risk factor, accelerating the onset of the failure itself. In cases of chronic valvular heart disease, dogs in advanced stages B2 and CD show significantly lower vitamin D levels than healthy control dogs. This negative correlation indicates that vitamin D status is tied directly to the degree of pathological remodeling happening within the cardiac tissue. We see an equally aggressive correlation when we look at cellular mutation and oncology. When a dog's serum calcidiol concentration drops below 40 nanograms per milliliter, clinical data shows a sharply increased relative risk of cancer development. Furthermore, applying therapeutic supplementation to elevate those levels improves the dog's physiological response to ongoing cancer therapies. Chronic vitamin D deficiency functions as an active catalyst for systemic cellular failure, driving disease progression in both the heart and the oncology ward. The active hormone is also required to modulate immune function and suppress systemic inflammation. Gastroenterology panels reveal that dogs suffering from chronic enteropathy consistently present with depleted serum calcidiol concentrations. In a retrospective study analyzing 43 dogs with protein-losing enteropathy, low vitamin D was significantly and directly associated with fatal clinical outcomes. Similarly, in immune-mediated disease, these low serum concentrations directly correlate with decreased overall survival times. Veterinary clinicians now utilize this specific metric as a prognostic biomarker to predict survival odds and inform treatment plans for pet owners. Without adequate calcitriol, a dog's gut and immune system lose the ability to regulate severe inflammation, turning otherwise treatable enteropathies into fatal events. Translating this metabolic science into practical reality requires looking at how dogs are actually fed, particularly in regions like India, where the homemade diet is a cultural standard. A standard homemade canine diet typically consists of chapati, rice, and milk, with occasional additions of boiled chicken or breadcrumbs. When analyzed against the nutritional standards set by the NRC, AAFCO, and FEDIAF, these specific ingredients are actually severely deficient. Owners frequently assume dairy provides the necessary nutrients, but cow's milk is actually an exceptionally poor source of vitamin D for canines. While summer milk is slightly richer than winter milk, neither contains enough density to bridge the gap and hit the 100 to 120 nanogram target. Because these staple foods lack the necessary cholecalciferol, dogs restricted to this diet are practically guaranteed to develop subclinical hormonal insufficiency. A diet that feels wholesome and natural to a human is entirely incompatible with the systemic metabolic needs of an obligate dietary consumer. Preventing these systemic pathologies requires pet owners to actively audit their dog's diet and introduce hyperdense sources of vitamin D. This chart compares vitamin D density in dietary interventions. A 17-gram boiled egg yolk provides a baseline of 37.1 IU. When substituting fish, variance is extreme. Species like rohu offer 84 IU. By contrast, the mola carplet provides 93,122 IU in that weight, orders of magnitude higher. If precise raw dietary adjustment isn't feasible, owners must rely on commercial formulations like cod liver oil syrups or highly palatable veterinary supplements like Nutrich to strictly meet AAFC requirements. Dogs cannot absorb health from the sun. Veterinary medicine must stop treating vitamin D strictly as a bone-building accessory and prescribe it for what it is, the essential hormone for canine longevity.